Hello, am I audible? Hello, am I audible? Hello, you are mute, by the way, so you can't talk. So I think you have to unmute in order to talk. Hello, hello, hello. My system is broken. So today I'm going to discuss about the collocated grid arrangement, and after that I'm going for the assignment that I've given yesterday. That one I will show you how to do it. And at last, I'm planning to go for some pipe flow simulation in ANSYS Fluent, so that can be done. So to give you a brief exposure of how the commercial solver works. So going to that of the colloquial grid arrangement. So how many people have joined? So let us redo the or let us now discretize for collocated grid arrangement. And the collocated grid arrangement typically works like, so for example, if this one is basically P, which is my cell of interest, and capital E and capital W are basically the cells centered at the east and the western part of the P itself. So uh, this is small w and this is small e, and this is capital W. So this is WW. So since a collocated grid arrangement we are following, so therefore the U and P both are solved at the same are solved at the same cell centroid, and the equation for UP will be, which is we are getting from the discretization of the Navier-Stokes equation, that will be APUP equals to ANB UNB UNB plus BP plus half of PW minus PE multiplied by area. So A is basically the area of the cross section. So if it's a domain like this, so this area is basically what? So this one is basically dy into dz. So this is equal to dA, and if this one is basically your x-axis. So now let us go for the continuity equation, and this we also have to discretize on the this control volume itself. So discretization of continuity equation So going to the discretization itself, so AEUP equals to, so this one is not the one. So similarly, the continuity equation is basically rho UEAE is basically equal to rho EW, AW equal to 0, or EV equals to UW, where the east surface and the west surface, if the density is same and the area of cross section is not changing, then the velocity at both the surfaces are basically the same. So EV and EW are not available directly. Basically, you have to express this EV and EW as a function of the neighborhood cell centroids. And similarly, another thing I also forgot to write is basically if I go for AEV, when I'm going for the discretization of the Navier-Stokes equation, E equals to A N B U N B plus BE plus PP minus PEE multiplied by area divided by 2. So UV is basically equal to A N B U N B plus BE divided by A plus PP minus PE D divided by 2, where D is basically what area of cross section divided by east cell coefficient. So this UP is basically similarly equal to A N B U N B plus BP divided by AP plus PW minus PE multiplied by dP divided by. So now we have discussed both the Navier-Stokes equation and the continuity equation itself. So as I've said earlier that one of the thing we should not do is basically this EV should not be expressed as a function of, or if I use a central difference formula, this EV is basically equal to UP plus UV divided by 2, and similarly U small w is equal to UW plus UP divided by 2. And let us concentrate on EV, and UP and EV are the expressions which are given previously, that I've shown previously. So EV is basically equal to UP plus UV divided by 2. So going to the expression itself, so this is equal to sigma of ANB UNB plus BP divided by AP plus half of PW minus PE multiplied by DP and plus of sigma of ANB UNB plus BE divided by AE plus half of PP minus PEE DE divided by 2. Okay. So therefore, then I actually go to EV equals to the final expression, that is ANB UNB plus BP divided by 2AP plus of half of, or one fourth of PW minus PE multiplied by DP. So plus of ANB UNB divided by 2 of AE, and this one is BE plus of one-fourth of PP minus PEE DE. So as I've said earlier, for example, if there is a checkerboard kind of an arrangement where this one is 10, this one is 100, and this one is 10 again. So this one is P, this one is E, this one is W, and this one is EE, which is 100 again. So this term will be PW minus PE. So PW minus PE will be equal to 0. So this will be one-fourth of DP 10 minus 10, which is equal to 0. And similarly, if I go to this one, so PP minus PEE, so 100 minus 100 multiplied by D divided by 4. So this will be equal to 0. So these are basically the terms which actually becomes insensitive to that of uh, the checkerboard kind of pressure arrangement that I've said earlier. So therefore, we should do some modifications in order to avoid it. So one of the modification that we did earlier was algorithmic basis. So that is called the simple algorithm. Another way of doing it is basically Rye and Chow interpolation. So basically, while discretizing this EV as a function of this EV plus EP divided by 2, we are going to introduce some correction terms so that this discretization actually becomes sensitive to that of the checkerboard arrangement of the pressure itself, and which is taken into account while discretizing the velocity of that of the getting the equation for the velocity after discretization of that of the Navier-Stokes equation. So those things we are taking into account by using this Rye and Chow interpolation. So these are the terms which are insensitive. So we should mathematically get rid of it. So insensitive terms, this term and this term, insensitive to insensitive to checkerboard arrangement of pressure. Okay. Similarly, if I go for a remedy, which is Rye and Chow interpolation, Rye and Chow interpolation, that is PP minus PE in the expression of EV, we must bring. So then EV is basically equal to not only EP plus EV divided by 2, but we are going to introduce some term which are minus of 1/4 of dp pw minus pe minus of 1/4 of de pp minus pe and plus of half of dp plus de pp minus pe. So this term we have to introduce in order to take into consideration the local effect of this term and this term. So instead of approximating this EP equals to only this term, that's EP plus EU divided by 2, we are introducing this three extra term. So one of the reason for that is basically to make it sensitive to that of the checkered board arrangement. And therefore, your EV actually becomes sigma of A and B UNB plus BP divided by A plus of BP divided by AP plus sigma of A and B UNB plus BE divided by E plus of 1/2 of dp plus d dp minus b. Okay, so typically what we are doing is basically we are putting the value of e and e here, and alongside this pw pp all the terms itself, and after expanding we actually get this term since this up and ev are given in the previous slide itself. So by putting the values here we actually get this equation. Okay, so in this way the this pp minus p, which is your arrangement like this 100 minus 10, this factor is taken into account. So this actually becomes what? Half of dp minus dp plus de 100 minus 10. So this one is not equal to 0. So which basically means that we are making it sensitive to that of the checkered board arrangement of the pressure itself. So in this way, EV is forced to be sensitive to Tp minus Pe, the velocity field is made sensitive to checkerboard pressure field. And this EV is basically equal to UP plus EV divided by 2 minus of 1/4. Uh, that I've already written. I don't have to write it again. So in line with the above expression. So if I draw the control volume diagram again, so which is this one is our along the axis, this one is P, this one is E, this one is W, this one is EE, and this one is WW. So UW is basically equal to that of UW plus UP divided by 2 minus of 1/4 DW. So PWW minus EP. Similarly, minus of 1/4 of dP PW minus PE plus of half of dW plus dP PW minus PP. And similarly, we know that what do you mean by EW and EP, which are shown above. So I'm writing it down again. Now setting UW equals to sigma of A and B evenly plus BW divided by AW plus PWW minus PP DW divided by 2. Another one is UP equals to sigma of A and B evenly. You can easily get this by the discretization of the Navier-Stokes equation in a general format. So these coefficients actually depend upon the discretization scheme I am using. So majorly I am making them independent of the, I'm writing them in a general format. So this actually leads to UW equals to A and B UNB plus BW 2AW plus A and B UNB plus BP by 2AP plus of half of DW plus DP BW minus BP. So therefore, this implementation actually makes it sensitive to that of the checkerboard arrangement. So similarly, PW and PP will be like 10 minus 100. So this is not becoming equal to 0. So therefore, this makes it sensitive to checkerboard pressure arrangement. So I hope it is okay until now. So we can also extend this thing to kind of unstructured grid also. So to implement Rao, Rai and Chow interpolation to unstructured grid to unstructured grid. So E equals to UP plus EV divided by 2 plus half of A by AP plus A by AE PP minus PE minus of 1/4 of A by AP, PW minus PE minus of 1/4 of A by A, PP minus PE. So this is equal to VP plus EV divided by 2 plus of half of delta VP by AP plus delta VE by AE, PP minus PE divided by delta X minus of half of delta VP by AP minus PE divided by 2 delta X. So then half of delta V AE PP minus PE 2 delta X. And then going to the EV itself. So this is equal to PP plus EV divided by 2. So it can be further written into coordinate independent format. So if we simplify it further, it can be written into half of delta VP AP plus delta V A and then PP minus PE multiplied by delta divided by delta X plus half of delta VP by AP grad of P E plus delta V divided by AE grad of P E dot E of zeta cap. So typically this one is W and this one is P, this one is E, this one is EE, and this one is your origin E equals to 0, and this one is E of zeta cap. So therefore, similarly, we can write it to be like, therefore, E equals to EP plus EV divided by 2, sorry, plus of half of delta VP by AP, delta VE by A, PP minus PE divided by delta A plus half of delta VP by AP grad of PP plus half of delta V by E grad of P E dot E of zeta. Okay. Therefore, similarly on unstructured grid, on unstructured grid, unstructured grid. So my unstructured grid looks like this. So this one, or and this one is capital P, this one is A, this one is in cap, and this one is E of zeta cap. So this can be written as at the face, this one is phase 1, and delta of zeta is basically your EA NAC. So U phase 1, that is the velocity at the cell phase itself, that is basically equal to UP vector plus EA vector dot n cap divided by 2 plus of half of delta Vp by Ap plus of delta Va by Aa Vp minus Va divided by delta zeta plus half of half should be inside. So delta Vp grad of P 2 plus delta Va Aa grad of P A dot E of zeta. So this gradient operation are basically calculated by using gradient reconstruction method. So typically you get option in the solver itself to how to calculate the gradient. So this is calculated by gradient reconstruction method. So now that's how you can actually apply this Rai and Chow interpolation for the on structured grid itself alongside the structured grid. So that's actually another way of kind of making the grid or making the momentum discretization sensitive to checkerboard oscillations. Okay, so that's how you can apply the Ryan-Chow interpolation both for the structured and the unstructured grid itself. So now basically I'm planning to go for the solving the assignment that I've given in the previous class itself. So how many of you have been able to solve the assignment that I've given in the previous day? Dhananjay, Pandiyaraj, Manikandan, any one of you have tried to solve the assignment that I've given in the previous class?
Actually,
Hello.
I have attempted last assignment. Yours one I only started. I could not complete it.
Okay. Pandiyaraj, hello.
Sir, in assignment 11, we got a code already, sir. But the answer solutions is different, sir. What can I do,
No, no,
sir?
no. Nee, assignment 11, I actually requested to share the PDF version. Okay.
Okay,
I
sir.
have no access to the assignment itself. So if any one of you can share the assignment with me, I can try solving it. But I have given an assignment in the previous class, which was using the affine scheme, which was a purely convective flow in a 2D domain. So I'm asking that whether you are able to solve it or not.
Okay, sir. Okay, sir.
So that thing you have tried or not?
Yeah, tried, sir. I tried, sir.
So did you got the solution that how it looked like the profile itself?
Yeah, solution, sir. But the solution is be a very different, sir. As per your
Uh,
solution for assignment 9 as well as 11, and I am getting the solution plots for different, sir.
so can you share your screen which assignment you are talking about?
I'm talking about assignment 9 and 11, sir, both.
No,
But
no, no.
both are
I have
same
given a
questions. But both are same
no,
questions.
no, no, no. Listen to me. I have given a separate assignment than those assignments. In the previous
Oh,
class itself, it was
yeah.
like a flow in a 2D domain where you basically had like there is a u velocity, there is a v velocity, and there is
I'm not
Dirichlet
right, sir.
boundary condition. That you have not tried, right?
Yeah, yes, sir, yes, sir.
Okay. So assignment 11, if you are having a problem, you can share it with me. Dhananjay actually pinged me, but the PDF was not shared with me. That I'm asking you repeatedly. But if you can make a PDF out of it and send it to me, I can try solving it.
Okay, sir.
So the assignment that I've given in the previous class, let me look into the assignment first. Yeah. So it was a domain like this. So the main reason was that some of the issue that we have with our point scheme. So phi equal to 100, phi equal to 100. So phi can be a scalar, that can be a temperature, that can be concentration. Leave it like that. So this one is we are having two velocity. One is basically v equal to 2 meter per second. Another one is u equals to 2 meter per second. And along this x-axis itself, which is a line which is joining the diagonals of the square. So that thing I want to plot the profile of the phi along the this x itself. So this one is phi, this one is x. So typically it should be like a step input itself, which is root 2 times of the domain length. So this one is a domain length itself. So root 2 divided by 2 multiplied by 8, which is basically L divided by root 2, 0.707. So this one is basically the domain, the analytical solution should be like, it should be 100 at the top. If it's actually starting from here, the origin starts from here. So it should be 100. And when it actually uh, process intersects the other diagonal, the secondary diagonal itself, so it drops to 0. So if it's a purely convective flow, the profile should be like that. If I draw with another color, so it should be like this, another step input, step down, and then going to this. So if I actually plot by using a point scheme, by using different grid resolution, for example, 10 cross 10, 100 cross 100, and 10 cross 10, 100 cross 100, and 1000 cross 1000. So it will be typically giving me some results like this. So it will look like this. So it will be different. So if you get some results like this, so typically means that we are getting some diffusion. Okay. So whether though the problem is purely convective in nature, but after solving due to numerical issue, we are seeing both convection and diffusion. Okay. Convection and diffusion we are observing for a purely convective problem, purely convective problem. But due to numerical artifacts. So this is called false diffusion. So we actually get an excess diffusion when we solve the whole thing by using appoint scheme. The appoint scheme was basically introduced to increase the transportiveness. But what happened was that with the transportiveness came false diffusion, which is undesirable in our problem. So therefore, this is actually one of the things I want to solve the equation by using appoint scheme programmatically, and then want to show you that whether this profile we are getting or not. So my equation will be like del dot rho b phi equal to 0. Okay. So this will be my equation, a purely convective one. So what I have to do is basically I have to discretize this in both an x and y direction. So this one is P, this one is E, this one is W, this one is north, this one is south. So here I will directly write the coefficient in the equation itself. So the homework goes to you to derive the coefficients and check whether what I've written is right or wrong. That is actually right, but I want you to derive on your own. So I think I should go to my share screen. I think I have an yeah. So screen what you want to share. The window. I think industry is open. Industry. So I think I can open MATLAB. This one is not. Yeah. Yeah. So can you see my screen?
Yes, sir. Yes, sir.
Uh,
Yes, sir.
okay, I got it. Uh, Should like that. I have to change into LAN in order to use it. Let me give a moment. I have to kind of unshare it and then I have to convert this into LAN, otherwise this will not. Ooh, let me open the MATLAB. Okay, now it's open. I think I can open a new worksheet. So, so clear, close all, and these things are clear all is basically used in order to clear your uh, the workbook itself, and then close all is basically clear off is basically kind of flush off for the memory. Close all is basically closing all the previous graph that you have plotted, and CLC is basically used for clearing the screen. So these things I basically write in the beginning, and then in points uh, x. So this is number of points that you want in the x and the y direction, which is same for your case, but I am now writing it to be different. But let me save it first. This one is basically here. Okay. And then this title. So endpoint x is basically your input, enter the value of index and good enough. In y and Then these are the number of points I'm basically want from the user input, and then domain length, which is basically 1 unit in my case, one, and hx is basically dom length divided by 10.x minus 1. And similarly, what I have to do is basically I have to so hy is basically your dom length divided by 10 points minus 1. So this is delta x and delta y. Good. So x actually is hx dom length. So this is basically giving you the y domain span, and y is basically 0 hy. Then let me see that. So this x and y is basically giving you the domain itself, so which actually starts from 0.11. So it is actually divided into 10. It actually ranges from 0 to 1, and there are 10 points you are seeing, 10 grid points. So that's how it works. And similarly, in the y direction, we will look into that. So hx is basically hx and xy are basically delta x and delta y, and the domain length is taken to be 1 unit. So that's how I'm defining delta x, delta y, and x and y itself. Then I'm initializing the problem, and यहाँ पर क्या काम करेगा, defining the domain problem domain. So this typically is a different thing. So initializing the problem is basically you're putting the boundary condition. So in underscore points x comma 1 is to in points y, which is basically equal to 0. So this you have to look into the problem, how it looks like, and accordingly I'm defining the boundary address. This is x, this is in points y. So typically this is also equal to, this should be uh, and similarly t1 comma 2 y equal to 100. Similarly, to go here and at to right side 1 is to 1 comma 1. So this is basically in 0.621 split point, and then t underscore new is basically in points. 1 is to 1 is to in steps. So this is the domain initialization. So let me look into the domain again. So it's access. So my domain actually is from 1 to context. This is wait for a minute. I have to look into the problem itself. So this actually ranges from, so this endpoint y, which is ranging from this 0 to 100. Y equals to, this is equal to y, and this is ranging 1, and this is ranging from, and this हम इसमें जाके y हो गया और 1 is to point xy करके xy हो गया, मतलब हाँ एक पे जाके y ने किया और सौ वाला तो ऊपर होगा। सौ वाला है 1 to 1 10 8.5 करके now it is. So these are basically the boundary conditions itself. So t is basically 1 to endpoint x and 1, which basically means that y equals to 1 and the x is given going from 1 to endpoint x, which is equal to 0 itself. So which is your lower part of the domain. Okay. And then it is endpoint x, which is the right hand side of the domain itself. And 1 is to endpoints y, which is actually going from top to bottom, from bottom to top. And right hand side and the top part is basically the right hand part is basically the temperature where it is ranging from 1 to endpoints y, which is from bottom to top. And similarly, 1 is to endpoint x, which is ranging, but endpoint 1 is constant, which is basically the topmost part. So that is basically 100. And similarly, what I'm doing is basically I'm doing domain initialization before solving the problem, because this problem I'm going to solve in an iterative manner. So this thing, that's why I'm doing. I'm basically putting temperature new value over the whole domain itself, and want to see after the initialization itself, I will iterate to the problem and see the temperature profile across that XX diagram. So now going to the problem itself. So parameter, define parameter. So which is basically rho equals to 1 and C equals to 1, V equals to 1 and gamma equals to 0. So which is your diffusion coefficient. So gamma. So this is by using R point scheme. R point scheme and discretizing. And so error equals to 1. I'm defining a variable because when I'm iterating, I have to look at the error. So iterations equals to 0. And while error is, so error is taken to be 1 so that it actually goes into the loop. So that's the intention of mine. So for I equals to 2 is to 1 is to n times minus 1. Since n point x is basically my boundary, so I'm not going to change the value there. So this is 2 is to 1 is to n points y minus 1 is, and for a underscore e equals to gamma, similarly a underscore w equals to gamma plus rho into u into hx. Similarly, a underscore e equals to gamma and gamma, and a underscore s equals to this to gamma plus rho into e into h y. A underscore p equals to so like सबको प्लस करके जो मिलेगा वही वाला होगा this plus this plus 4 into gamma plus. So t underscore new I comma j equals to a underscore p t I plus 1 j plus similarly aw over into t I minus 1 comma j. So a underscore in into t I plus 1 into j plus 1 similarly j underscore south equal into t of divided by a underscore south निकालते हैं उसके बाद ढूंढ दबाया so in my vibrations what we can get direction equal to iterations plus 1 theta equal to 0 for I equals to 2 is to 1 is to x is 1 for I equals to a for j equals to, which is your y directional counter, a y minus 1, which will calculate the error, so which is basically the difference between t and uh, t mu I comma j. So theta equal to theta plus tts t I j plus t minus 1 comma j. And t equals to t. Yeah. And similarly, this is my off point scheme itself, where I actually put the coefficients and then kind of uh, solve the temperature iteratively over the whole domain. So now I'm going to draw it. This is the hold on, read on, wall in equals to max size direct t direct. So this one is basically I'm just finding out the distance along the diagonal from the point along x. So which is your uh, minus 1 Vx minus 1 to hy 2 and this is your this one, hy, and then this one is in. And similarly for the temperature itself has to stored along the diagonal. 1:1:2 to the size of diagonal of T. Okay, diagonal of T, 1, 2, 3, 4, another one, and then this will be equal to in diag in equals to, which is storing the temperature along the diagonals. Then plot diagonal in diag. Color is not required. I can O. So X sticks are basically your 0 0.2, 0.4, 0.6, 0.8. So these are the pointings I'm giving you just for kind of practical. 0.4. Now we have to do this. So why I'm basically giving you the nomenclature of the X level and the Y level itself. Distance.
1 point went to 0.21.
Up, please. Hello.
X sticks point
Ah, now this way.
0.21 up. Yes.
1, 2. So this Y level is the value of the transport property. Transport property. And this title is upwind false. Then the analytical solution is basically have to put, which is your step input solution. Solution. So X is up to 1.4 because the whole length is basically 1.414. If the domain is 1, so do 2 times of it. That's why it is going to 1. So equals to space space 0, comma dome length will be 1.4 thousand points I want for A. So minus 1 is to max is offset. If Z of K is basically less than dome length points and 0.71 71 is equal to 100 equals to 0. Here, hold off region that right. Location, location of list and then put the limits. Limits basically so it's basically y limit 0 to 100 is data solving y level is basically Right. Please. अब मुझे थोड़ा सा डिबग करना पड़ेगा जहाँ जहाँ पर प्रॉब्लम हुआ है। debug it. So let me debug it. Line number 16 and admin. Are you able to see my screen, by the way?
No, sir. No, sir. No, no, sir.
No, no, it got out of it. Let me check it. Problem.
It has gone out, and the font is little smaller.
Okay, okay, I will come back, please. Bear with me. Uh, code count. Code count. So, share screen. So now the screen is visible, I hope so. Let's see.
Not yet. Now it is visible. So the font size is little smaller, sir.
Font size, you have to go for a bigger screen. You can't see on mobile and can do it because if I make it too big for you, it becomes difficult for me to write the code.
ठीक है.
So
Okay.
if I actually go for it, so it is 10 cross 10. So you will see that you are getting a profile like this. So this orange line is basically your analytical solution, and this blue line you are seeing, that is your numerical one. So if so, you can see a distance from the analytical solution itself. So here you are seeing a gradient at the interface where the two diagonals are intersecting with each other. Okay. So if I make the resolution to be a higher one, so which is 100 cross 100, so it will be a bit better. So now the blue line actually comes closer to that of the analytical solution. So by reducing the cell resolution itself, we can reduce the false diffusion. I think in this workstation, I can make it with 1000 cross 1000 also. Let us see how it works. 1000 cross 1000. It will take some time. So therefore, typically you are saying there is a kind of deviation between the numerical and analytical solution, though it's a purely convective process. So that is what we call it to be false diffusion. So I think it is going to take much more time. So let's stick to 100%. So this is called false diffusion. So typically when you are using a point scheme, so you are going to get some false diffusion, which is typically not present in your domain. So that was a problem that I tried to make you solve. I will share the code by the end of the day with you so that you can run in your PC and see that what is called false diffusion. So this is actually one of the most important things. So in case of a point scheme, though it is much more transportive compared to that of the central difference scheme itself, but it will result in false diffusion. Okay. So I think we can close this one out. So what I was thinking today, hello, am I audible?
Please share these contents also in your upload.
I will share in the chat itself the code. I will share with you by the end of the day. Okay.
Okay. Thank you, sir.
So another thing I was thinking was that I was kind of thinking of doing a pipe flow simulation today in SQL. So how many of you actually know that how to use ANSYS Fluent Solver? Hello. So ANSYS Fluent is typically a finite volume solver. So I'm going to the workbench itself. So I have 2021 R1 version installed in my PC. So what I'm trying to do is basically a pipe flow problem. Uh, so So will it be uncomfortable for you if I do a pipe flow simulation in ANSYS Fluent in this class? Dhananjay Pandya.
You can you can do it, sir, but some beeping sound is coming continuously.
But you have to do it yourself in order to understand the solver. Okay. I may be doing it without thinking much, uh, so that it actually becomes a kind of reflex for me. But I don't know what's the case with you. You may do some error while doing it. But I will make you understand how it works. So as you can see my workbench window. So first, what I'm going to do is basically click on the mesh itself. So I think
Is this a free version, sir, or
you can download the student version, but this one is a licensed one. So what I'm using.
and
So
the
this one is
contents
not
of
the
student version is more or less comparable with this version, or there is a large amount of truncation?
meaning. Both of them are basically more or less same. At least the problem I'm dealing with. The cell count limitation is there. I think 5 lakh cell count limitation is there in the student version, but that cell count level I'm not going as of now since you are
Any
explaining.
special computing requirement is there for
No, no,
normally?
no, 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 no. You can run it on a laptop. I think in the meantime, you can switch off your mic. When you want to talk, you can switch it on and then you can talk it. So going to the geometry itself. So geometry is actually the section where you kind of create your own geometry. And after that, you have to mesh it. So mesh are basically, I've shown you the control volume itself where I divide the whole domain into stencils or point itself. So going to the geometry. So this one is basically your space claim geometry. So there are two options. Either you can create it in design modular or space claim itself. So one thing I'm planning is basically going it for space claim. So
There is some continuous beeping sound. I don't know from where it is coming.
there is no beeping sound from my. Yes, there is a beeping sound because of the UPS in our system. So there is a inverter in our lab. So that's why a beeping sound is coming. Sorry for it, but I can't get rid of it. So
We
that's how the
understand.
space claim. Yeah. So that's how the space claim looks like. So this one is a y-axis, this one is a x-axis, and this one is a z-axis itself. So if I want to make it a 2D domain, so one thing I will do is basically draw the whole thing in XY plane. So in order to do that, I have to click on this gizmo and this Z point itself, and then I have to select on this one, this plane, select new sketch plane. So this thing you just go through. When you install your software, you will get all the options. So you can click on that one and then you can draw it on your own. Okay. So this one is a preliminary one. You can just sit and watch. It is not required from my side to catch it up as you see. So what I'm doing is basically I'm making a domain of about 1000 millimeter by 100 millimeter. So making it a rectangular domain like this, a rectangular slab itself. So then if I go to this one, this actually becomes a plane. Okay. So this one is basically this one is your wall. So if I go to the selection itself, this one is a wall, this one is a wall, this one is an inlet, and this one is outlet. So what we are going to do is basically we are going to simulate the pipe flow, the flow of water through the domain. And this one is a 2D problem. So this we are going to solve by using simple algorithm. Okay, is it clear to all of you? So at the wall, we are going to impose a no-slip boundary condition. Okay, so this one is a rectangular slab, by the way. Is it clear to all of you?
Yes, sir.
Okay. So then going to that of the, then I have to save it, and there's no requirement of saving it. I can go directly to the workbench and then go to mesh. So right click on the mesh, I have to click on the edit itself, the edit button. It's up there. Mm, it's let's click on edit again. So now you can see the domain here. So this one is your domain. So the rectangular domain itself. So what you have to do is basically mesh the geometry. So before meshing, you have to go to physics reference and convert that into CFD. So which is basically your fluent input file. So that you can basically read it from the fluent itself, and then you can go to mesh and then go to method and select from the geometry itself, and then you can make it to be multi-zone, and then you have to select on this pre-mesh type, which is basically quadrilateral. Okay. So as of now, I am basically selecting very specific options, which I also want you to do so, because multiple options, creating multiple combinations will give you multiple kind of meshing. So that complexity I'm avoiding as of now. So now you can see that the whole domain is divided into these control volumes. So I've actually made you learn in the class that how to, now I've solved it for the 2D problem, that how to solve for the 2D problem, purely convective problem by using affine scheme. So that was not a coupled one. So it was like a general transport equation, del dot rho v phi equal to 0. But this one, we are solving the continuity and the momentum equation in a coupled manner. So if I want to select the number of cells in the direction, I have to go to mesh, then go to insert, and then go to sizing. And then I have to select from here the edges itself. So this one is one edge, this one is another edge. And then click on this apply. And then type, I have to go for number of divisions. So number of divisions, I will go for 200. And then I can go to hard. And similarly, since I'm going for the meshing along the wall edges, the two edges of the wall itself, I will also go for the sizing in the inlet and the outlet, and then going to that of the number of divisions, and this is 20 and this is hard, and then go to mesh, and now you can see that I have meshed the whole domain into these tenses. So I have to go for certain kind of mesh resolvement in order to capture the flow physics. So I've said earlier that near the cell faces, near the walls also, you have to go for grid refinement, which is called the biasing. So as of now, the grid itself is kind of sufficiently fine in order to go for a uniform mesh. Biasing itself is not required, but if the mesh is not so much fine, we have to go for biasing. So this kind of things actually comes with experience. So is it clear up till now?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Okay. So now you have to go for the cell edges itself. So this one and this one you have to select and place on in on your keyboard, and this is wall, and this one is in, and this is inlet, and this one is in, and this is outlet. So the name selection, under the name selection dialog, you actually see the wall which is colored by red, and this one is an inlet, and this one is a outlet. So then what you have to do is basically you have to go to export, you have to go to mesh, you have to go to fluent, and then you have to go to export. So if I actually create a file like this in the desktop, that which is called pipe. So now you can create a mesh file like this, mesh pipe dot msh. So this actually gets saved, and then what you can do is basically you can go to read, and then you can go to mesh, and both this data itself, and then you can replace mesh. So this is a Fluent solver. So I actually launched it previously in order to kind of block the license. Otherwise, there is a license problem. So you can click on this one, and then you can get the solver. So if I go to display, you actually see a domain like this. So it's depending upon the name itself, it's already showing that this one is an inlet and this one is an outlet. Okay. So there are multiple tabs. So as of now, the I am doing this flow solving up till now as of today's class. So what I'm doing is basically I created the domain, and then I meshed the domain by using workbench meshing, and then I imported that into the Fluent solver. So in the next class itself, I will kind of explain that how the whole Fluent solver basically works. Okay. So is it cleared up till now?
Yes, sir.
Okay. So I think we can stop our class because this understanding this Fluent solver will take 1.5 to 2 hours. So I think we can do it in the next class itself. So where I will explain that how the whole thing works, and I will also re-go through the that space claim and also the workbench machine. Okay. So I think we can stop as of now.
Okay, sir.
Oh,
Thank you, sir. Thank you, sir.
okay.